Hi, today we learned to integrate functions on curves in general metric spaces. And as you see, we are getting close to the end of this series. We went in depth, we went deep, and we went wide, covered a lot of stuff, as you can see. Please watch those videos as well. And also please subscribe if you are following the content anyway. With that, let's recall how we were introduced to integrating functions and vector fields along curves. That was back in calculus, if you remember, and we learned to compute work for a particle that is moving in the presence of some force field. There are some other applications from physics as well. The integrals I'm talking about, I will write down and you will recognize them immediately. Another very important application of integrating along curves, called contour integrals in this case, is in complex analysis. For example, in the very statements of Cauchy's integral theorem and also residue theorem, you integrate a complex valued function along a curve, usually a closed curve in the plane. Also, you don't have to go into complex world to do integration along the boundaries. Green's theorem, which relates an integral along the boundary of a nice domain to a different integral inside the domain, uses the notion of course, integration along the boundary. What we do today is to give meaning to line integrals on rectifiable curves in any metric space. So we are not dependent on any structure. Then we want to see its connection to the Hausdorff-1 measure, if we can recover that integration from integrating against dH1. And finally, we touch upon this very, very deep and modern and fascinating application of the concept of integration along curves to the theory of Sobolev functions. Okay, so if X here was my Euclidean space and G was a continuous function, then you would recognize this as the definition of line integrals. That was how we were told to compute line integrals back in calculus. And the definition, here's the definition, and notation here is important. So gamma is the curve, and we use ds, important, not dH1 as it will be later. All of this here is one unit of notation, and G here is some Borel non-negative function, infinity value also allowed. Borel guarantees that this integral will be well defined, that this function will be measurable. So you have a rectifiable curve, you can parameterize it, and here we need to have absolutely continuous parameterization, but we also have better, we always have Lipschitz parameterizations, which we will assume. So if you start with the rectifiable curve with this length of gamma finite by definition, then you can parameterize it, say Lipschitz, and then this quantity here you take to be the definition of this. Of course, one needs to prove that this quantity is independent of the parameterization, but that is just a change of variables for integrals between intervals of R1. So it's a R1 problem. One has to follow carefully what reparameterizations mean and how to transition between them. That's not something we're going to do. So here is the definition of integrating a Borel function along a rectifiable curve. And the important notion here is that of the speed of the curve. For Euclidean target space, if X is Rn, this is just, you take gamma prime of t as a vector, which exists almost everywhere by Rademacher's theorem, and then you take its norm. But we have mentioned this many times, and we have done 2 videos actually on the subject, that even if you are mapping into a very arbitrary metric space with no linear structure, you can still make sense of the speed of a curve. And it's well defined almost everywhere, which is enough for us to integrate that. Okay, that's our definition of line integrals. If you don't like to see this notion of speed or metric derivative involved, there is a way to avoid that. If you have a rectifiable curve, we can always reparameterize it by arc length. That it was probably our second video. And if gamma subscript s, so this s is not like this ds, it's just a coincidence. So gamma s, if gamma s is the, if there's only one, is the arc length parameterization of some curve, then the line integral we defined previously can be also computed through this quantity. So the difference here is that there is no gamma s prime of t. And the reason, in fact, is that if you are parameterized by arc length, then this speed, in fact, is 1 almost everywhere. But that is a claim that needs to be proven. But the take-home message is that we can take this to be the definition of line integral. Then the other definition becomes the lemma. But the benefit, again, is that here there is no other notion beyond calculus, no metric speed. Okay. So now we know what integration along a rectifiable curve is. Our second objective was to relate it to integration against Hausdorff measure. So for that, I need to recall some notation and some facts that we previously covered. So with capital gamma, we refer to the image, or also called trace, of a curve. So this is a subset of the target space X. And we had this multiplicity function, or Banach indicatrix function. I also mentioned historically why it is called this, which counts the number of times you hit a certain point on the curve, right? It counts over coverings. So for this point, the multiplicity is probably 3. You hit that point 3 times. For this point, it's 2. For such a point, it's only 1. And so on. And if you're off your curve, then it's 0. If you integrated speed of a curve, you recovered the length of the curve. That was proven, or that is usually proven together with proving that gamma prime, in fact, exists almost everywhere. So that is that part. But then our previous video covered this part, that also that quantity equals integrating against Hausdorff measure this multiplicity function on the curve gamma. And these, although equal quantities, are very different creatures. So this is an integration on the line, on real line. This is an integration on the metric space and on the curve of some function. So here you have multiplicity function counting the overlaps. If you integrate that function against the H1, it ends up being equal to the length of the curve. One particular corollary of this is that H1 of the image is less than the length of the curve, because H1 is integrating 1 against the H1, but multiplicity is bigger than or equal to 1. And it's strictly bigger than 1 if the curve is non-injective. This all makes sense because, for example, if you have this curve and this part is covered twice, so let me use this red. So the curve covered this part twice. And let me also orient my curve so you can imagine more easily how it travels. So it goes this way, it comes back, makes a loop, covers itself again on this section, and then continues this way. So multiplicity on this red part from here to here is 2 and is 1 otherwise. So for the computation of length, this red part will be counted twice, but H1, just as a subset, doesn't see that that red part has been covered twice. That is how this becomes strict. And also this indicates that if you are injective, then these quantities become equal. So the difference, it's important to keep this in mind, that the difference between length and H1 of the image is exactly due to the parts where we have double covers. And if you integrate instead of 1, this multiplicity, that detects all these overlaps and you end up being equal. So if you integrate 1, you only get H1 of gamma. If you integrate multiplicity, you get H1 with multiplicity, which ends up being equal to length. So what does this have to do with the line integral? So from the previous fact that if you integrate speed, it equals integral of multiplicity, we mentioned that you can extend it to Borel function. So if you integrate a Borel function on the image of the curve, you can pull it back to the interval AB, and if you integrate it against speed, you recover that. So this all we had covered. If you haven't seen those videos, please go watch them. So this is a true fact. But then this one is exactly the definition of line integral, this quantity here. So this by definition equals this, and by this is now theorem, by theorem, therefore we put these together and we get this theorem that for Lipschitz curves and Borel functions G, integral, line integral is integrating against dH1, except that you have to bring in the multiplicity. And in particular, if your curve is injective, then this line integral is nothing other than integrating against dH1 along the image of the curve. So if you drop this multiplicity, so this was injective case, if you drop the multiplicity function here, you get a smaller integral because G is non-negative, so you go smaller. Therefore, if you integrate G without N, so G times 1 instead of G times multiplicity, you get a smaller quantity. And both of these quantities, by the way, are important. So sometimes you want to integrate with respect to parameterization. Sometimes you want to integrate with respect to the image of the curve, and you don't care if this has been covered twice or 3 times. So these are quite different notions. So this is integrating on a subset of the metric space, some function, but this one is integrating, this is basically an integration on the interval AB of the pullback of G. Depending on context and what you need to do with the line integral, or just this integral, you use either the left or the right quantity. But here's the connection between them, and also that if you plug in multiplicity here, it all becomes the same. Okay, now we know 2 ways of integrating functions, scalar functions on curves. What good is it? So other than all the applications in the classical setting that we saw, an amazing one that is quite recent, this business all started after maybe 1990s, well after 1990s, I wanted to say 1995, 6, the major results probably appeared just around the turn of the century. But here is a very, very quick and cartoonish picture of what it is about. So if you have, you start with the simple, not simple, well, classical observation. If you have a C1 function on a Euclidean domain, then for every rectifiable curve, you can also say for every C1 curve, for example, We have this inequality from fundamental theorem of calculus, but done the right way. So this to get this, you need some simple yet beautiful tricks from calculus, multivariable vector calculus, how to do chain rule for the derivative, and a few inequalities, like if you integrate a vector and then take norm, it's less than first taking the norm and integrating the scalar, things like that. So here you would look at u composed with gamma as a real valued function on the interval AB. And we know this is how to deal with such functions. This is like the simplest thing that we learn in calculus. So we have a C1 function from AB, and we have fundamental theorem of calculus. So you apply it to, so value at B minus value at A equals, in fact, integral of derivative. And that's where this derivative comes in, and the chain rule. So this becomes derivative of U times derivative of gamma, this one. And that inequality I showed you kicks in, and this becomes inequality, and we have this. So, but by definition, this is nothing other than the line integral of absolute value of gamma, nabla gamma, nabla u, the gradient of u. So the more important than what this how this is proven is what it says. It says that no matter what curves you have, whether it is this curve or this curve or this curve, the difference between the end values, here gamma b, here's gamma a, is less than integrating this gradient along those curves. So pick any curve that joins these two, integrate it along the curve, and its value is bounded from below by this difference. When you pass into Sobolev functions, similar thing holds, except that you, in a very precise sense, you have to allow some exceptional curves where it fails. But anyway, all of a sudden we realize that all of this now uses only very basic properties of Euclidean spaces. We can just define it in any metric space. So we say a Borel function. So this will be our gradient u. A Borel function is an upper gradient of another function u. So we want to, the end point is that this rho is kind of the derivative of u, but only kind of. So we say rho is an upper gradient of a function if we have this inequality, just the analogous inequality here, for every rectifiable curve in your metric space. And this, of course, doesn't need to be unique. If you have rho, then maybe you multiply by 2. Again, it's an upper gradient. You add 3, it's again an upper gradient. Of course, then one talks about minimal upper gradient, smallest of these, and stuff like that. Again, I'm not presenting the rigorous theory here, just giving you a hint of what we can do with line integrals. So all of this now is for a general metric space X, and we can talk about upper gradients in such generality. Based on this observation, there have been slightly different classes of Sobolev functions that have been introduced on metric measure spaces. So we always had metric space. Now there comes in the measure. So where does measure play a role? So for Sobolev functions, you need to assume some integrability. And when you want to talk about integration on a metric space, you want to have a measure. So Hausdorff measures are a built-in class of functions, measures on a metric space, but often actually you have X the metric D, and it's completely different, not necessarily relevant to D measure on that, with some properties, of course, you want to do stuff. Now, the thing is that for quite general and generous assumptions that are not too restrictive, these classes of functions end up being quite interesting. And for Euclidean spaces, just this abstract approach ends up giving us the usual Sobolev spaces. So a Sobolev space, roughly in this setting, will be a function U that has an upper gradient rho, such that rho is now integrable in LP, for example, LP of X with respect to this measure mu. We can also assume some integrability on U itself, for example, U measurable and integrable, or locally integrable, things like that. So that will be the type of Sobolev functions we're talking about. And see how abstract and general this is. So compare it to how you study Sobolev functions in Euclidean spaces. You take derivatives, partial derivatives. You have characterization through absolute continuity on almost every line. Any proof you do with Sobolev spaces in Euclidean spaces uses Fubini's theorem, because you foliate your space. And none of this works in general metric space. You don't have a built-in or natural canonical coordinate system on a metric space. You don't have foliation like that will allow Fubini's theorem stuff. If you look at the Sobolev theory in Euclidean space, you will assume that it heavily relies on the structures of the Euclidean space, but this is saying no. In fact, you can construct Sobolev functions through this approach, and then, of course, it's a difficult result to show that what you have now, the class of functions you have, agrees with the usual Sobolev class. And also, you need to prove that the upper gradient, or the minimal upper gradient for a function in your abstract Sobolev space, in fact, is nothing other than gradient of U absolute value that disagrees with that. So we built a very abstract theory that agrees with our usual theory in Euclidean settings, but the benefit is that we can now do this. We can talk about Sobolev functions on fractals. We can talk about Sobolev functions on snowflakes, on counter sets, on any crazy space you can imagine. Sometimes it is an interesting class, sometimes it's empty and not. Yeah, okay. So if you want a reference for this, and the title already has it all in it, is this recent book. Well, it had to be recent because, as I said, this theory isn't that that old. So late Heinonen, he's passed away, Pekka, Nagis, Shanmugulingam, and Jeremy Tyson. All of these people I have been fortunate to meet in person, and their book, their amazing book, which covers all of it. The thing about this beautiful book, it's a monograph, is that it goes very slow and covers everything in detail. Yeah, so check that out if you are interested in such stuff, or if you are looking for a research field to maybe pick up. That brings us to the end of this video. Thanks for staying with me so far. Have a wonderful time and hope to see you in our next video.